Hello, welcome back. Today we're going to continue our discussion about the first derivative test. And you might recall yesterday we talked about the first derivative and some things that we learned. One, if the derivative is positive, then on an open interval, then we're saying that the function f of x is increasing. Remember, you got to spell it out. And if the derivative is negative in our domain, then we say that the function f of x is decreasing. We want to avoid the following words. Avoid the word it, the graph, anything like that. You want to be specific. We don't like those. Talk about the function, say f of x. And then lastly, if the derivative is 0, then we're saying f of x is constant. And this has a lot of applications for us that we'll talk about later on. So again, the first derivative test, we saw this yesterday. If C is let C be a critical number like a pirate. C be a critical number of a function. Now we've talked about critical numbers before. That is where the derivative is 0 or D and E. Then on an open interval, if the function is differentiable on the interval except at C, then we can a point can be classified as the following. If the derivative changes from positive to negative, then we can say that that point, that our critical number is a relative maximum. And if the slope is changing from a negative to a positive at that point, then we can say our critical number is a relative minimum. In other words, if our slope goes from positive to negative, we have a maximum value, and if the slope goes down to a positive, we have a minimum value at that critical number. Very easy to do. So let's practice a few more. We saw these a little bit yesterday, so we're going to practice a few more. But for the first one, obviously we have a piecewise function. We want to find all the relative maximums and minimums. And we want to find out where the function is increasing and decreasing. So we're going to first take the derivative. But first of all, I want to see if this is continuous. You always want to make sure this is continuous. Is f of x continuous? And to do that, all I really have to do, it does have a value. I just want to make sure that the limit from the left equals the limit from the right. So if I plug negative 1 into the first function, I'm going to get, what's that? Negative 2 plus 1, or negative 1. If I plug it into the bottom one, I'm going to get 1 minus 2, or negative 1. So they're meeting each other, so this is going to be a continuous function. And now I want to find out the derivative. So taking the derivatives here, f prime of x, we are going to get 2 for x is less than or equal to, sorry, not equal to, but just less than. When you take the derivative of a piecewise function, we don't include the endpoint, so we just go less than negative 1. Take the derivative here, we get 2x, and this is going to be for x is greater than negative 1. Like so. So my only critical number it looks like I might have, it looks to be at negative 1. So my critical number, there's nowhere where the slope is going to be 0 except at 0 here. So if I find my critical numbers, 1, I say where's the derivative equal to 0. If I set both of these equal to 0, 2 equal to 0, well, that's not going to happen. But 2x equals 0, yep, I'm going to get x equals 0. So 0 is a critical number. But I also have to find out where the derivative does not exist. And this is a little bit more interesting in terms of this problem. Because if I want to find out where the derivative does not exist, on 2, not going to happen. But on the bottom here, I get 2x. So if I plug in negative 1 to the top, if I want to find the derivative at negative 1, for the top, the derivative is just going to be 2. But at the bottom, it's going to be negative 2. So if you notice, this is going to form like a corner for us at x equals negative 1. So it's kind of like this. At x equals negative 1, on the left, we're approaching a slope of 2, and on the right, our slope is going to -2. So it's going to form kind of a corner there. It's not smooth. It's not differentiable necessarily. So in other words, this is not going to be differentiable here. So when I do my sign charts are going to be, my critical numbers are going to be 0 and -1. Those are my critical numbers. So -1, 0, my first derivative, followed by my second derivative. Before -1, I know my slope. I'm just going to plug it in here. Before -1, my slope is just going to be 2. So it's positive. So it's increasing, going up. Between -1 and 0, it's going to put me over here. So if I plug in like a -1/2 here, it's going to give me a negative value. So if I plug -1/2 into the bottom, 2 times -1/2, 2 times a -1/2, right? That's going to become -1, so it's negative, so it's decreasing. Plugging anything bigger than 0, again, I am on this one as well. Like plugging anything bigger than 0, that's going to be positive. It's going up. So I can answer the question now. We can say f of x, we're going to write it down this way, f of x is increasing on the domain -infinity to -1 or 0 to infinity because the derivative is positive. Likewise, we can then say f of x is decreasing. Oops, that's terrible looking. F of x is decreasing on -1 to 0, and that is because the derivative is less than 0. We have a relative up here. We have a relative maximum at -1. So we can say f of x has a relative max at x equals -1, and that is because our rule from yesterday, or from today, the slope goes from positive to negative. We go from positive to negative, so it's going to be a relative max because, not by, because the derivative goes from positive to negative, and f of x has a relative minimum at x equals 0, and that is because the derivative goes from negative to positive. And there's our answer right there. Whew, that took a while. I hope you guys enjoyed this video. Go to video number 2. We'll take a look at a few more examples. I'll see you then.